Hi, I want to show you how you can use a vector network analyzer to perform time domain refractometry measurements. And this is a great tool to get information about the impedance of PCB traces and also to localize changes of the impedance along the trace. So let's first set up the VNA. So make sure that you start at the lowest possible frequency, and for best spatial resolution use the maximum bandwidth of your device. To get the visualization, which you would also get from a TDR measurement, so first go into the transform menu, enable the transformation and set it to a low pass step function. So this will correspond to the step function of a TDR measurement device. And now we need to set the format correct. So we want to show the resistance and the scale should be 20 ohm per diff. So, and now you see nothing, but that is because there's an open connection on the VNA. But now if I attach an SMA cable, you see the line goes down. And now we can look here. So here the cable has around 50 ohm, and here this edge tells that the cable is unterminated, so the end has an infinite resistance. So this can be now used to inspect traces with different widths and characterize their impedance. So let's start first with the smallest trace, and then we can set a marker here and see that we can set a marker here and see that the impedance is around 100 ohm. And also the trace is unterminated, what you can see in the rise of the impedance at the end. So the next trace, it has a width of 1 millimeter, and let's connect it. So here you see the impedance comes much closer to 50 ohm. At the end of the trace there's also 50 ohm termination, so that's why here the trace is flat. And this trace looks already good, but if you look closely you see it's slightly above the 50 ohm of the cable and of the termination resistance. So let's go to the next. It is 1.2 millimeter wide, and this is also the optimum design parameter for getting 50 ohms. So now you see here the value of this trace. It's very close to the 50 ohm termination resistor and 50 ohm cable. And you see here these two bumps. That is when the signal passes through the SMA connector, where the impedance is not fully matched. Now we can go to a more wide trace. So this is slightly too wide, and as you can see the impedance is even lower. And if the trace is much too wide, so in this case 5 millimeter wide, the impedance drops down to a very low value, And in this case there's also no termination, so you see then the signal that's reflected from the back of the trace and then jumps to a higher value, because the signal which is traveling on this trace gets also reflected from the SMA connector side, and only after the second pass all signal is returned and the information that this trace is unterminated can be seen. So the next trace, it has a discontinuity, so there's a bend with not optimal design, and let's see if that can be also seen from the VNA measurement. And yeah, if you look closely, I will move the marker away, you can see that there's a slight dip in the impedance. Now I have a second board with the same traces, and let's also measure this. So I will connect again the optimal microstrip line with, and now as you can see, suddenly there's a change in the impedance, and here it's the SMA connector, here it's somewhere the termination resistance, so it's in the middle of the trace. And now if you look closely, you see the trace looks perfectly fine, but there must be something different in the center of this trace, and you will immediately see if I flip the trace around. So I have cut it in the center of the trace, just the return plane for the signal, and this changed the impedance. And now let's connect it back to the nano VNA, because now I can show a cool thing. So probably you have heard that the signal on the return plane travels underneath the trace, and I have now a drill bit and can reconnect the ground plane. So let's first do it on the side of the trace. So if I connect here, you can see there's still small difference in the impedance, but if I put it right under the trace, you can see how it completely disappears, and so the return current can now travel its preferred way under the trace. I think that's quite cool that this can be done with a vector network analyzer, and see you next time.